Good evening everyone, I am Mr. Ish. Thank you for joining me. In this video we're looking here at the regular triangular pyramid frustum volume. It's a difficult one and it's confusing, but it's also at the same time very fun. It requires a reconciliation procedure at the very end because you can come up with two different volume formulas for the frustum of the regular triangular pyramid where the cross sections will be regular triangles. Here's a complete regular triangular pyramid. We'll slice it off from the top and you'll end up with the frustum. You know, at the very top you can have a small triangle. We can call that capital A, which would have the sides A. Here on the bottom you have a larger triangle forming. We can call that capital B, and its sides can be designated with a lowercase b. In all instances, when you're taking slices over here, there'll always be a equilateral triangle. You'll integrate the area of this from a lower limit to an upper limit based on dx or dy, whatever it is, you'll get your volume. That's the procedure it will take. But how will we determine the area of one of these cross-sectional sliced triangles? It's going to follow pretty much the path of the square pyramid frustum video that you've already seen. And let's bring all of this into play. You have here a certain dimension which we can put like this to get the effect of this line and how it interacts with the height of the frustum. The convergence you see here from the triangle slices in the base towards the top, they're obviously becoming smaller because you're narrowing your solid towards the top. You can represent all of that here, b comma 0, and you will have here a comma h. You have to determine the equation of this line because this will feed in to the dimensions, you can say s, all around to determine the area of that triangle. We're trying to determine that side s, and that'll help us get the area of the slice, which we will integrate. What will be the equation of this? It will be very much similar to the equations you've seen for the other frustum solids in the other videos. You'll have here a slope going to be minus h over b minus a. Y is equal to minus h over b minus a x plus a y-intercept. You have to find that out. Obviously you're going to put b and 0 in places of x and y, and what are you going to get? You're going to get here an hb over b minus a. When you do all of that computation, you'll get that, but you're solving here for x. X is going to be equal to, take the y-intercept on the other side, flip the slope factor here, affect everything by means of the minus. You're going to get hb over b minus a minus y times your slope factor, which is flipped around. It's reciprocal. That's what it is. You can clean it out. X is equal to, open up all of this. You'll have here a b minus y times b minus a over h. That's going to be representing here the side of each of those triangles. Now we have this. We'll save it right over here. B minus y times b minus a over h. You don't need to see any of this anymore. Now we have to actually do the hard work. With this equation, which you know x equals all of that, which I also mentioned previously, it's equal to the s, the side of each of those triangles. How do we use it? We use it to determine the area of the cross-sectional slice, which will integrate for your volume determination. If each of these represents a side, you're looking at something. This right here is equal to a side, but when we're bringing in a bisecting line, and you know everything here is a regular triangle, which means everything always has to be equilateral, then you're bringing the 30, 60, 90 triangles into play. This here is s, this here is s over 2, and the height must be determined. I'm just using this height, don't confuse this h for this. It's just me using the triangle area terminology, half, base, and height. Anyhow, this right here represents s, and then s over 2 will be b minus y times b minus a over h over 2. This right here will be this part right here, s over 2. What will height be? It will be a root 3 factor because you have 1 root 3, 2 in terms of 30, 60, and 90. The height is opposing the 60. What are this base is? It's root 3 of that. So the height is going to be root 3 of this. Now I've determined my height. This here represents my height. Originally I was calling it my b over 2, but I've converted into h because h over here is root 3 of b over 2. H is equal to b over 2 root 3. This was my base, half of a base, and then I'm looking opposite with regards to 60 degrees, so it's root 3 b over 2. Now we have everything which is coming into play to determine the area of that slice. Area of that slice is area of a triangle, which is half times base. The base is the entire s dimension, not s over 2, but the entire s dimension, which is equal to this. b minus y times b minus a over h times the height, which is this b minus y times b minus a over h. You see this over 2 and you see this root 3 over 2. I can bring them outside as this. There's nothing wrong with me shifting this here and making it a root 3 over 2, which I bring out here on the side. 1 over 2 times root 3 over 2, combine them, root 3 over 4. I have the same item multiplied by the same item is like a binomial. We can make it into b square plus y square b minus a whole square over h square. This is a minus b whole square, a square plus b square minus 2ab. That's exactly what we're doing. 2by b minus a over h. What does all of this fancy expression represent? It represents the area of each of these triangles, which can now integrate from a lower limit 0 to the height of your frustum, which is h. The only thing you want to bring out of this is root 3 over 4, but if you focus on this right here, it looks exactly like what you saw in the square pyramid volume frustum derivation, exactly the same thing. And all of this right here will give you exactly the same outcome as a square pyramid volume, the frustum formula, except this will be on top of that. Let's bring all of this here, b square plus y square b minus a whole square over h square minus 2by b minus a over h, all of this with respect to dy. Now, it doesn't make sense for me to integrate all of this by means of the algebra. You can look at the previous video, the square pyramid volume frustum derivation video. This integrand is exactly the same as that, except we have this. From all of this, if you remember that video, what you ended up seeing was an h over 3 times a square plus ab plus b square. That was the volume of a square pyramid frustum. Now when we're talking about a regular triangular pyramid, you have this come on top of it, and it's this volume is equal to, you compute it, you'll have h over 4 root 3 times a square plus ab plus b square, and this right here represents the volume of a regular triangular pyramid frustum. Me having skipped these intermediate steps because I've shown them, they're exactly the same in that other video, the square pyramid volume frustum video. I'll include the tag for that. This here is a formula that we're getting from this derivation procedure, where h represents height, a here represents a side of smaller triangle, and I'm going to show you all of this because this is where the reconciliation procedure is needed. b equals the side of larger triangle. When you look at a frustum, it looks something like this, like here. This right here is a larger triangle, this here is a smaller triangle. The dimensions here I'm calling a, which you're talking about and seeing over here, these are the b. So this here is the formula I'm getting here, where you actually plug in the side length dimensions, and I'm using the word length here. Generally, length can imply the a's and the b's. The other formula which you will commonly see in textbooks for the same solid will be this, h over 3 times a plus b plus root ab. Now look at the differences over here. This is where the reconciliation is needed. Here we don't have lowercase, we have capital. Here a represents the area of this small triangle. Here we're talking about sides, here we're talking about area. B will represent the area of the large triangle. H here is just the height in terms of a dimension. It's no different than this. Now we need to reconcile between these two, and I will show you. And this right here I consider to be the better formula than this, because most of the times you're given actual dimensions of sides and you have the ready hand formula already available, versus this where you're putting in or inputting area figures or area numerical values rather than the actual side dimensions. Your reconciliation will be like this. When you're looking at this small frustum triangle on the top, we know it's called A. It's also made up of a half base, and I'm using the full word here so we don't start repeating letters which have been used before. It's made up of a half base and a height, but I know I was giving everything here because it's equilateral triangle a side of A. Now what would be the base over here? Well, it's obviously going to be that full base, but what will be the height? Again, you think back to 1 root 3 2, your trigonometric ratio. It'll be a over 2 root 3. What will the area equal to? It will be equal to a square root 3 over 4. Now let's put this aside And let's talk about this. When we're looking at the lower triangular pyramid base, it's the larger base and it's made up of the B sides. And when we're talking about the capital B, we're talking about this. It's made up of a half and it's made up of a base and a height. But what will be the base? It will be exactly one of these lowercase b's, and obviously trigonometric ratio comes back. It will be b over 2 root 3 the height. Compute all of this. This will be equal to your base dimension. You'll have a b square root 3 over 4. So I have this and I have this. Now look at this formula and let's start plugging in the items. I'm removing all of this because you know what it means. There's an h over 3 sitting outside. You have an a, which is represented by the area a square root 3 over 4. You have a capital B, the base area, which is represented by that, b square root 3 over 4. Remember, this right here represents the product of the two bases under the square root. These are the individual sums of those bases, the upper, the lower, the product of the upper and the lower under a square root times h over 3. Now we'll bring in these two in terms of the products. A square times b square is an a square b square. Root 3 times root 3 is a 3, 4 times 4 is a 16. You have to compute all of this. You'll have h over 3, a square root 3 over 4 plus b square root 3 over 4 plus isolate what you can. You're going to bring out an ab over 4. That's what you'll have. ab over 4 and a root 3. What can you isolate from all of this? You can isolate the root 3 over 4 from each of these items, and you will do that. H over 3 times root 3 over 4. You'll have here an a square plus b square plus ab. If you simplify all of this, this radical will convert this into this. You'll have a h over root 3 4, or you can say h over 4 root 3. H over 4 root 3 a square plus b square plus ab, which is exactly what you're seeing over here. So the reconciliation procedure is completed. Remember, this is the formula I had gotten from my integral calculus procedure. This is the more common formula. Remember, in this formula you have the ability to put in the sides, a's and the b's. Here you are actually placing in the values of the areas of those upper and the lower frustum faces, the large and the smaller triangle areas of the faces, and you compute with the areas. Here you compute with the sides. So you can decide which of these formulas is better. Here's an h over 3, here's an h over 4 root 3, and then the differences in the parentheses. But that right there is the end of this video. The regular triangular pyramid frustum volume derived for you. Both of these volume procedures are good. Thank you for watching.